Mr. William, today has been exhausting, man. I just taught for 8 hours. Now with the shoot.
Yeah, you look tired, team.
I am exhausted. I'm gonna, let me go and freshen up first before the shoot.
Okay, sure, I'll wait for you. Go ahead. Well, Mr. Team looks really tired. Let's freshen him up a little bit, shall we? I have an idea. Waitress, can I have a lemon, please? Thank you for that. Alright, so I have a lemon over here. I'm gonna squeeze it in. I'm sure that's gonna wake him up. Come on. Okay, shh. Waitress! Thank you very much. Shh.
Man. Oh, okay, come. Let's do this.
Yes, okay, you look better.
Yeah.
Come, get a drink.
Yeah. It looks a bit.
No, it's okay.
Oh my god. What was that, William?
Oh, I was just trying to aid you. Lemonade.
Oh my god. I can't feel my tongue. Are we still friends? So, Mr. William, why was that lemon so sour just now?
Well, it's because all fruits, including lemons, they will contain this functional group which is called the carboxylic acid. And all acids are sour. That's why it gave you a very good aid, doesn't it? Right, and carboxylic acid, it turns out, is the focus of today's lesson. So shall we go into details with them? Right, everybody, we need you to take out your encyclopedia and let's go into action right now. Now, today we're going to study about carboxylic acid. Carboxylic acid contains what we call the carboxyl or the COOH functional group. Now, what you must know is the general formula. Either you can call this CnH2n plus 1 COH or CnH2nO2. Now, Mr. Tim, let's discuss carboxylic acid. You do notice it looks like a combination of two functional groups that we have studied previously, right?
Yeah. I can see a carbonyl functional group, that's C double bond O.
Yep.
And I can also see that hydroxyl functional group, OH.
Yep.
Yeah.
Right, so even though it looks like there are two different functional groups, what happens right now is there's an interaction between these two groups. Right, so let's discuss why is there interaction between the two groups. To understand this, you have to return back to the concept of orbital overlap. Alright, so let's draw this together. So we have our C double bond O together with OH. Now, as you can imagine, C double bond O, there will be a pi bond that runs across the C double bond O. And Mr. Tim, if you look at the oxygen, do you think there will be an orbital that's adjacent or on it?
Yeah, probably, because the oxygen has a lone pair. So the lone pair will be also found in the p orbital.
Right.
And now these two p orbitals here that you see, they are number 1, they are parallel, and number 2, they are adjacent. So they will sideway overlap, right?
Yep. So once you have all these orbitals, they're parallel, they're adjacent, what you expect is you expect an orbital overlap between them, and there are two regions, one on top and one below the plane. So this is what we meant by the interaction between the two functional groups, which therefore allows the delocalization of electrons. Right? So when we study carboxylic acid, it is not carbonyl, it is not hydroxyl, rather it's something very different, right, which we will discuss with you in greater details. Alright, Mr. Tim, before we go into the reactions with them for carboxylic acid, actually this chapter is a very important connection point, right? Because there will be a lot of reactions that's interconnected between the different chapters. Now, let's ask the class, right? Do they know how many reactions are involved in carboxylic acid? Alright, let's make a guess. Haha, you are wrong!
Alright students, so in carboxylic acids, right, we have a total of 19 reactions, and out of the 19, 8 of them, we're going to learn how to prepare carboxylic acids alone, alright? So let's take a look at the first one, reaction 7.4. So what we have here is a primary alcohol, and we're going to oxidize it to a carboxylic acid, alright? Remind yourself what a primary alcohol is. The carbon, bonded to the OH group, Mr. William, is bonded to how many R groups?
Just one if it's primary.
Just one, right? So we have a primary alcohol here, and guys, I want you guys to recall, when you oxidize a primary alcohol, it's a two-step oxidation. It becomes an aldehyde first. You have that C double bond O, H functional group, and you can oxidize again to give you a carboxylic acid. Okay? Now, the reagents are important for this, right? We have to, if you want to oxidize a primary alcohol all the way to carboxylic acid, we need to use a strong oxidizing agent. And what is that, Mr. William?
KMNO₄.
KMNO₄, right? Now, if you want to use a weak oxidizing agent, now here's the thing. If you want to use K₂Cr₂O₄, then you have to make sure that you heat under reflux. Okay, so it goes all the way. Now, Mr. William, can you remind me, right? let's say if I wanted to stop at the aldehyde, I wanted to stop here, right? So I'm going to use a weak oxidizing agent.
Yep.
What conditions do I have to use?
We also have to distill because we're trying to do a controlled oxidation. So we kind of stop the oxidation halfway before it goes on to the carboxylic acid.
Exactly, which is exactly what we see here, right? So if you want to stop at the aldehyde, weak OA, K₂Cr₂O₄, and like what Mr. Williams said, immediate distillation, okay? Now, in carboxylic acids, it gets a little bit more tougher, so we can see that some carboxylic acids can actually oxidize further, and one of them is your very famous methanoic acid. Now, I'm going to run through this with you guys. Now, remember what we saw in hydroxyls. To oxidize an alcohol, we will go to the carbon, okay, involved in the functional group here. So in this case, it's your COOH functional group. Go to that CH bond with me, and we're going to slot in an oxygen there, okay? Remind yourself, we saw this in hydroxyls, right? And when we slot in the oxygen there, Mr. William, you can see that in this compound here, you have two OH groups bonded to the same carbon. Is this stable?
No, it's not stable. It kind of follows very similarly to the geminal diol.
Exactly, right? So it's like a geminal diol. So what's going to happen now is that you're going to eliminate water. You're going to spontaneously remove water. So circle the water molecule with me. Circle the HO, circle the H, get rid of the water molecule. Now, if you take a close look, what do you have left, Mr. Willem? We see this CO2, right? What is that?
Carbon dioxide.
Carbon dioxide, right? So it becomes CO2 and water. Now, Mr. Willem, could you bring me through the next one?
Yeah, of course. So guys, just remember, carboxylic acid, typically, they are not able to be further oxidized. There are two of them. Mr. Tim went through the first one. Now, the second one is a very special carboxylic acid. Now, we call this ethane dioic acid. Right, as the name suggests, it is a two-carbon backbone. So there's carbon 1, there's carbon 2. Now, when you see a structure like this, just be mindful, it is not stable. So it will also further undergo oxidation. Now, how does this work? It's a little bit more complex. You can see that there is like some sort of a cleavage, right? Yep. So we're gonna kind of chop this away. And what happens is you're gonna add one more oxygen. Right, so imagine we have one oxygen over here, and this oxygen is going to take the two hydrogens away. All right, so I'm just going to color code this. You will see that what you have formed is you actually have H₂O, and whatever that's left behind will be two molecules of CO2. And that's how it works. And bear in mind, only KMNO₄ is able to do this oxidation. Cr₂O₄, they are too weak to perform this oxidation. Alright guys, the second reaction that is able to form carboxylic acid is a bit linked to what Mr. Tim just went through earlier on. It is the further oxidation of aldehyde into carboxylic acid. Right, so just remind yourself, once we have an aldehyde, if you do an oxidation, simply add one oxygen onto the H and there you will get a carboxylic acid. Again, using oxidizing agents like Cr₂O₄ or KMNO₄.
Yep. Now, so in reaction 5.6, we're going to see here now is again preparation of carboxylic acids, but from here, we're going to take a nitrile functional group, right? Your C triple bond N bonded to an R group. We're going to convert it to carboxylic acid. Now guys, recall this, right? We have hydrolysis here. Now Mr. William, can you remind me, right? What does lysis mean?
Lysis means you're going to break.
Yeah, so we're going to break this. So do this with me. We have seen this before. Go to that nitrile functional group. Break it for me, okay? We're going to cut that open. I'm going to do this above with you. So after we break it open, it looks like this. Now hydro means
water,
right? So what I'm going to do now is I'm going to put in water molecules. In fact, I'm going to put in two. So we have OOH and NH3. Okay, so this is basically hydrolysis. Now notice how I've not factored in the conditions yet. So Mr. William, if there are acidic conditions, H+, who do you think reacts with the H+?
Acids will be sensitive to bases, alright? So anything that's basic will further react with the H+. So in our case, it's going to be ammonia.
That becomes NH4+, okay? Now in the case of an basic condition, then that's where the acid steps in, and the acid reacts with the base. Acid plus base gives you salt and water, right? So in this case, you just get your salt, and of course, the ammonia doesn't react with the base, so ammonia stays ammonia. Okay? That's it. So this is reaction 5.6.
Now, another reaction that you should be very familiar with, and we kind of learned this a long time ago, is in alkenes. All right. So what happens here is we are doing oxidative cleavage, right? So as you can see here, when you put in KMNO₄, you're expected to chop the CC double bond. All right. And if you follow portion by portion, now the left-hand side, the R1 and the R2, the general rules that we have taught them before is once you cleave this, you generally will replace with
oxygen, yeah?
Yes, with oxygen. All right, so let's do this together. You will see that you have your R1 carbon with R2, and you replace this with an oxygen. While on the other side, which I'm going to code this as green, and what do we have here is we have your R3 bonded to carbon with an oxygen with a H. Now, what is the difference? You get two different types of products, right?
So one of them has a CH bond and the other one does not. So this is your ketone versus aldehyde again.
Right?
Yeah.
So are ketones able to further undergo oxidation?
No, because I don't see a CH bond there.
Yes, you're right. All right, so you can see this ketone basically are inert to further oxidation, and that's why this is the final product. While over here, you have an aldehyde. And aldehydes, as we have learned many times today, they will be further oxidized towards a carboxylic acid. All right, so these are reactions that we have learned before. Try to recall this.
Okay. Now, guys, again, we gotta dig back our memory, okay? So this one, again, we have seen this in arenes, right? So this is your side chain oxidation of an arene, or methylbenzene in this case. Now, remind yourself, to oxidize a benzene molecule, you need to tell yourself that the carbon that is bonded to the benzene, it needs to at least have one CH bond, right? That is your requirement, okay? So if you look at your methylbenzene here, or your alkyl benzenes here, focus on the carbon with me. I'm going to highlight this with you. Notice how this carbon, there's at least one CH bond. These carbons here, directly bonded to the benzene, also have at least one CH bond. Now, when we do side chain oxidation, this is what happens. This carbon that is directly bonded to the benzene ring, Mr. William, what does it become?
It becomes a carboxylic acid.
Yeah, and all the other, let's say if I have dangling carbons, right? What do all the other carbons become?
You're gonna chop them away, and they'll just become CO2.
Yeah, right? So I'm just going to focus on this guy. That guy becomes COH, and everything else, chop, it becomes CO2. So I see 3 extra carbons here. You just get 3 CO2 molecules, right? That's it. So don't forget, right? Your byproduct is also water, H₂O, okay? And that's it for reaction 4.6. Not too bad. Yeah? Alright, so again, very quickly, just remind yourself the condition for side chain oxidation, like I said, the carbon that is directly bonded to the benzene ring must have at least one CH bond. So, Mr. William, do you see a CH bond? Yeah?
Nope, there's no H.
Yeah. So you cannot oxidize this guy. No oxidation happens. Okay?
All right, and also one just small thing maybe to remind everybody is when you write the observations, there are always 2 things to discuss, isn't it? What are the 2 things?
Yeah, so you need to remember, guys, we're using strong oxidizing agent here, KMNO₄. So it will turn from purple to colorless. That is the first observation. And the second thing is this. This is what we have here, a benzoic acid. And Mr. William, remind me, a benzoic acid is what color?
It's white, it's a white precipitate.
So it's a precipitate that is white in color. Remember that. Okay? And that's it for reaction 4.6.
Alright, the next reaction is reaction 12.1. Alright guys, this is a new reaction which we will be learning, I think in lesson 3. That about right, lesson 3. So I'm going to give you a quick idea how this reaction works. Now the main idea is for us to change this functional group called the ester functional group. Now ester will look something like this, a C double bond O with another oxygen onto it. And what's going to happen is you're going to chop the esters away. Alright, so you're going to cleave this. Now the way that you cleave the ester, you can either use acidic or basic condition. And the end result is you will get either a carboxylic acid or the corresponding salt together with the alcohol, right? It may sound a little bit new, so why not we do this? We just break it down to 2 portions, right? If you focus on the cleavage area, you will notice one portion, we're going to put this in blue, right? The blue portion, as you can see, it turns out into either a carboxylic acid or a salt. Full details we explained to you in lesson 3. And on the other side, you do notice that the R2 together with the oxygen, it actually changes into the alcohol. Yep, so for now, just take it as a cleavage. You're going to form these 2 products, and that's reaction 12.1.
Now, Mr. William, before we move on, right, I got a curveball for you.
Okay.
Why is it that this alcohol, why doesn't it not react with the acid or the base?
Well, because alcohols, they are neutral, remember guys? They are neutral, right? Only phenols or carboxylic acid, they are acidic enough to do a reaction with bases. Alcohols are neutral, so they will never be sensitive to the acidic or basic conditions.
Very smart, Mr. William, very smart. Okay, now in reaction 11.1, yet again is a brand new functional group that you have not seen before, right? We call this an acyl chloride. And remind yourself, acyl is this C double bond O. So you have an acyl and literally have a chloride here. So this reaction is called, once again, hydrolysis. So do this with me. We're going to lysis first, this CCl bond. And I'm going to break this part into 2 parts again. So we have this R, C double bond O, okay? Then we have a Cl here, and again, hydro, meaning water. So I'm going to put in a water molecule. Let's do it together. So I'll go OH and H, right? H₂O, okay? So this is exactly what we have here. The hydrolysis of the acyl chloride gives you that carboxylic acid and also that HCl molecule there, all right? And this can be done at room temperature and pressure, okay?
All right, now the next reaction, it has importance in this reaction because if you focus on the carbon chain before and after, you do notice that the final product, there's one carbon shorter than before, and we will term this as a step-down reaction, which is kind of like the opposite of a step-up reaction. Now, Mr. Tim, can you remind them what's a step-up reaction?
Step up. So I'm increasing the number of carbons by one, or increase the number of carbons.
Yes, that's right. And this is a step-down reaction. So you have one carbon shorter before and after. Now, there are very few reactions that are step-up or step-down in the syllabus. So the moment you see them, really be mindful. All right, and we have learned the two step-down reactions. Now, one of them is through your, we call this a methyl alcohol functional group. Not every alcohol can do this reaction. Now, you must have a specific template, right? So what is non-negotiable? There must be a methyl group present, there must be a H, there must be a OH, and the only thing that can be different is different types of R, which can be different types of carbon, different types of hydrogen. But every time you see a structure like this, we call this a methyl alcohol. What we're going to do is we're just going to chop this away. All right, so you can see the CH3, once it's being chopped away, you're going to form this. And what is this, Mr. Tim, again?
We call this a triiodomethane precipitate, which is yellow in color.
Yep, right. So you're going to get a triiodomethane. And what happens to the other side, all right, so if you just focus on the backbone, now what we're going to do is we are actually going to oxidize them away, right? So once you do the oxidation, you will be forming the carboxylic acid. Right? So the key thing is to really focus on the carbon backbone. So you notice we have an R bonded to the carbon. That backbone doesn't change. Just ensure you have a carboxylic acid. And this carboxylic acid, because it's acidic, will therefore further react with the basic environment. So this is basically an acid-base reaction, right? So by the end of the acid-base reaction, you are going to form the corresponding carboxylate salts. All right? So the second one is through a ketone functional group, right? Or a carbonyl functional group. Again, you're going to have the methyl group that's present, right? We're going to chop this away, and the CH3 will become CHI3, which is the yellow precipitate. And what happens to the left-hand side, right? Again, you're just going to oxidize it into the carboxylic acid, and through the acid-base reaction, you are going to end up with the corresponding salts. Right, so guys, just remember, right, this reaction is uniquely different. First of all, it's a step down. Now, secondly, is the conditions, right? We don't do it under the usual strong heating. We do it under warming. And what is the reason for that?
Well, because if you look at your CHI3, right, guys, so I will draw this out with you. So if you draw this out, now, iodine is very, very fat. Yes, this is the only time it's okay to fat shame, okay? Iodine is very, very fat. So I want you to draw these electron clouds with me. They are so massively big, right? And when you have very big electron clouds next to each other, steric hindrance. So Mr. Williams, stable?
No, not very stable.
No. So the moment you heat it, it breaks down. Okay, so no heating, you need to make sure you warm it. Okay?
Yep, and once it's broken down, then you won't be able to see the yellow precipitate anymore. So I think the whole idea is to ensure that CHI3 will still be stable, we can still observe it, and therefore we can write down the observation as a confirmation test.
Correct. Hey students, so that were the 8 reactions that we just saw on how to prepare carboxylic acids. We're going to wrap things up, okay, by talking about acidity of carboxylic acid. So let's go. All right. Now, before we begin, Mr. William, tell me, are carboxylic acids strong or weak acids?
Carboxylic acid, they are organic acids, and organic acids are those that contains carbon. Generally, organic acids, they are weak acids in nature.
Right. So if they're weak acids, guys, they dissociate partially in water, not fully. So don't you dare write a full arrow. You write a reversible arrow, okay? So an acid here, dissociating partially in water to release H+, and the conjugate base. Now, if you guys can remember, a conjugate base and an acid, they differ by a H+, okay? So this is what we call the conjugate base anion. Now, Mr. William, if I want to have a strong acid, do you think my position of equilibrium should be favored to the right or to the left?
If you want a strong acid, I think the first thing is you're going to produce a lot of H+. right? So to produce a lot of H+, what you require is the position of equilibrium to be more favored towards the right-hand side, right? And that's why it becomes a stronger acid in nature.
Okay.
And what affects that? Why does certain equilibrium lie more towards the right-hand side?
Well, if I want my POE to lie towards the right, then I need to find a way to make sure that my conjugate base is more stable, right? Now here's the thing, Mr. William. If you look at this conjugate base, I see a negative charge there.
Yep.
Are charged species ever stable?
Anything that's charged is never going to be stable.
No. So if I want my conjugate base to be more stable, so my POE can push to the right, I need to find a way to disperse this negative charge, okay? And this is exactly why our lovely tutors in class will talk to you about the more stable this conjugate base becomes, the more my POE pushes to the right, okay? And the stronger my acid is. Alright students, so that's it. For this comparing acidity portion, we won't do it here. We'll let our lovely tutors in class bring you through. Alright, so that's it.
No, Tim. No, we are not ending yet. Alright, before we end,
Okay.
I have a challenge for you.
Challenge?
Yes. Are you man enough to increase our acidity?
I think, come, let's do it. Yes, I am.
Okay, here's a cheers to acidity.